In this video, we're going to be looking at the equations of motion. And what they do is they help us find information about any moving object. So we take these 5 bits of information, the displacement, the initial and final velocities, the acceleration, and the time, and we use these 4 equations. Now, sometimes these are referred to kinematic equations from the Greek origins, and sometimes they're also referred to as SUVAT equations, which is just an acronym of the 5 things that we use here. Now, in a typical SUVAT problem, what will happen is we'll be given enough information to replace 3 of our variables with numbers, and we'll be typically asked to find a 4th thing. So based on what information we're given, we're going to need to decide on which SUVAT equation to use. Something that can catch us out, make sure that we're using standard units. So if we're told a displacement, make sure it's in meters. If we're given a time, make sure it's in seconds, and so on. Now let's jump straight into an example. We've got a race car moving at 50 meters per second. It's 1,000 meters away from the finish line. It accelerates at a constant rate and it passes through the finish line at 80 meters per second. We're trying to work out how long it took for this section of the journey. Now feel free to pause the video and unpause whenever you're ready to take a go. Now the 50 meters per second refers to the initial velocity of the race car. The 1,000 meters is of course a displacement, and the 80 meters per second is a final velocity. How long is a question of time. So in this case we have S, U, V and T, and we do know it's accelerating, but the actual value of A is not important in this case. So we need to choose an equation which uses this combination of letters S, U, V and T, and I believe we can opt for this second equation here. So what we'll do is we'll substitute these numbers in and we'll rearrange the equation to get T. And when you do that, you get a value of T which works out as around about 15.4 seconds. Now, sometimes rather than 3 numerical values being explicitly given, we might have to infer some information. Something that crops up a lot is an object being at rest, which implies the velocity is 0. And it could be an initial velocity of 0, it could be an object starting at rest, or it might be an object coming to a stop, coming to rest, which would imply that the final velocity is 0. If an object is dropped, that also implies that there's no initial velocity and that the acceleration that the object will experience is due to gravity. There's a specific value of gravity that we always use, and that is 9.8 meters per second on this planet at least. So whenever an object is dropped or thrown, you can infer that the acceleration is 9.8. Now let's have a look at a second example. We've got a 10 kilogram object being dropped from a 100-meter tall building. And we want to know how fast it is traveling the instant it hits the ground. Now, something in this question is here to throw you off, and that is the 10 kilograms. Galileo found out that the time of descent, it does not depend on mass at all. So that was the famous sort of 2 spheres experiment there. Again, pause the video if you want to have a go at it yourself, and unpause it whenever you're ready to take a look at the answer. Now, if an object is dropped, it implies that the initial velocity is 0, but it also implies that the acceleration due to gravity is 9.8 meters per second squared. The 100 meters is clearly a displacement. And if we want to know how fast it is traveling, we're looking to find a velocity. So the letters that we're working with are S, U, V and A. Time in this case is not important. So the SUVAT that we can choose, which uses S, U, V and A, is the bottom equation here. And once again, we can plug in the values and we can rearrange the equation to get a value of v at around about 44 meters per second.